Ever wonder what's lurking at the very heart of our own galaxy for decades? We've known about Sagittarius A asterisk, the supermassive black hole that sits at the center of the Milky Way. It's a cosmic giant, a gravitational monster, but it's also shrouded in mystery, hidden behind thick clouds of cosmic dust and gas. But now, thanks to the incredible power of the James Webb Space Telescope, we've just peeled back a layer of that mystery, witnessing something never seen before. Recently, astronomers pointed the James Webb Telescope, or JWST, towards our galactic center and caught something spectacular, a fleeting 40-minute flare of light bursting from the vicinity of Sagittarius A asterisk. Now, flares have been seen before, but this one was different. It was observed in mid-infrared light. Why is that a big deal? Well, think of it like this: trying to see the galactic center. Invisible light is like trying to see through a dense fog, but mid-infrared light cuts right through the cosmic dust, giving us an unprecedented, crystal clear view of the action happening right at the edge of the black hole. This groundbreaking observation, made on April 6th, 2024, is like having a brand new set of eyes to study these enigmatic objects. It allows scientists to track the flare's brightness over time, giving them vital clues about the chaotic environment swirling around the black hole. A team led by researcher Sebastiano von Fellenberg analyzed the data and noticed a distinct pattern. This wasn't just random flickering, it was a structured event, suggesting powerful, organized forces are at play. So what's causing these brilliant flashes of light? The leading theory is a process called magnetic reconnection. Imagine the area around Sagittarius asterisk as a tangled web of incredibly strong magnetic field lines. Sometimes, these lines can snap, twist, and then violently reconnect, releasing a colossal amount of energy in an instant. It's like a cosmic short circuit, and that sudden burst of energy is what we see as a flare. The new JWST data strongly supports this idea. It seems the same super-fast electrons that generate light in other wavelengths are also responsible for this mid-infrared flash. This connection paints a much clearer picture of the physics at work. It's not just random turbulence. It's a specific, powerful mechanism that's lighting up the darkness. By modeling the data, the research team estimated that the magnetic fields in the flaring region are incredibly intense, somewhere between 40 to 70 Gauss. To put that in perspective, Earth's magnetic field is about half a Gauss. These super strong fields are powerful enough to accelerate particles to nearly the speed of light, generating the high-energy radiation that our telescopes detect. Understanding this process is key to figuring out how black holes release energy and influence their immediate surroundings. What is even more fascinating is when we combine these new infrared observations with data from other telescopes. For instance, astronomers have long observed Sagittarius A asterisk using radio telescopes. When they compared the timing of the JWST infrared flare with radio signals from the submillimeter array, they found something intriguing: a potential delay of about 10 minutes between the infrared flash and the radio emission. This time lag could be the smoking gun for understanding how energy travels through the system. The infrared light might be coming from the initial super hot explosion, while the radio waves are generated a little later, as the particles cool down and interact with the surrounding material. It's like seeing the lightning flash before you hear the thunder. This multi-wavelength approach is like putting together a puzzle, where each piece of data from a different telescope gives us a more complete picture of the event. As the flare fades, the light it emits changes, shifting to longer wavelengths. The JWST's data beautifully captures this process, showing us how the high-energy electrons lose their steam over time. It has a direct look at the cooling process in one of the most extreme environments in the universe. We can literally watch the aftermath of the explosion in real time. This helps scientists refine their models of how matter and energy behave under the immense gravitational pull of a black hole. This discovery is more than just a single observation. It's the beginning of a whole new chapter in black hole research. One of the biggest questions is whether this 10-minute delay between infrared and radio signals is a consistent feature of all flares, or if it changes depending on the size and nature of the event. By continuing to pair the JWST with radio observatories, we can start to map the flow of energy in and around Sagittarius A with unprecedented detail. But the implications go even further. Understanding our own galaxy's central black hole helps us understand all supermassive black holes. These cosmic titans are found at the center of nearly every large galaxy, and they play a crucial role in how galaxies form and evolve over billions of years. How do they affect star formation? How do they control the flow of gas and dust? How do they shape the very structure of their host galaxies? These are the grand questions that astronomers are trying to answer. The unique window provided by mid-infrared astronomy is bringing us closer to those answers than ever before. With every new flare we catch and every new piece of data we analyze, the mysterious, dark heart of our galaxy becomes just a little bit brighter. The secrets of Sagittarius A are starting to be revealed, and the James Webb Space Telescope is leading the charge. Thanks for joining us on this journey to the center of the Milky Way. If you're as fascinated by these cosmic mysteries as we are, make sure to hit that subscribe button and ring the bell so you do miss our next deep dive into the wonders of the universe. See you next time.